Rocks contain sedimentary structures, physical features that developed during or shortly after deposition of the sediment. Most sedimentary structures form through the interaction of moving water and loose grains of sediment. For example, when a stream moves sand along its bed, the size of the particles that can be moved will be limited by the strength of the flow. Only those particles small enough to be moved by the flow will do so. Larger particles will be left behind. In this way, sediment is sorted by size as the water interacts with it. Environments with sustained high levels of wave energy, such as beaches, therefore typically produce sediments that are well sorted, meaning that little size variation among particles exists. Generally, moderate to high levels of wind energy typical of many desert environments similarly produces well-sorted sand. In addition to sorting the sediment by moving the grains, beach waves and desert winds will organize the sediment grains and produce sedimentary structures. Both sand dunes in a desert and sediment ripples in a stream are examples of sedimentary structures. Many sedimentary structures, like desert sand dunes, form little by little, as the wind current sorts and moves the sand into piles. As they are formed, many structures develop an internal architecture in addition to their external morphology. This internal architecture can provide important clues about how the sediment was transported and deposited to geologists examining ancient sedimentary rocks in cross-section. Because sedimentary rocks form at Earth's surface, sedimentary structures and other features of sedimentary rocks also contain clues about environmental conditions at Earth's surface when the rocks were formed. The most obvious and common sedimentary structure is bedding, or stratification, layering that develops as sediment is deposited. Bedding forms because sediment accumulates layer by layer, with short pauses in sediment deposition represented by the surfaces separating individual beds. Many beds of sandstone contain cross-bedding, in which sets of small beds are inclined to the main sedimentary layering. Cross-bedding forms in many environments where wind or water transports and deposits sediment. The wind and water currents organize the sand into semi-parallel ridges called dunes. Continuous flow of water and wind causes sand grains to be eroded off the more gently sloping side of the dune that faces upstream, and these sand grains travel in the current to the brink of the dune. There, the sediment avalanches down the steep side of the dune that faces downstream. The inclined layer of sediment that results from the avalanche forms a crossbed. As the dune develops through time, such avalanches form sets of crossbeds, an internal structure recognizable to the geologist. Figure 3.27b. In most cases, only the crossbeds of a sediment dune are preserved. The dune's original external morphology typically is eroded away and not preserved, so it is the crossbeds that provide the clue to the geologist. Ripple marks are small ridges and troughs that are similar to dunes in that they form through organized movement and sorting of loose sediment grains by a moving flow. You commonly see ripples in shallow streams and around lake shorelines. The external morphology of ripple marks is commonly preserved along the bedding planes of ancient sandstone. Like dunes, ripples also have characteristic internal structures called ripple cross-lamination that are recognizable in cross-sections of ancient rock where the bedding planes are not exposed. Ripple marks can form either by currents moving in a single direction, as in a stream, or by currents moving back and forth, as in a shallow lake where sand on the bottom is pushed forward and backward by waves on the lake surface. Mud cracks are irregular polygonal downward tapering cracks that form when mud shrinks as it dries out. They indicate that the mud dried up after being deposited in water. Mud cracks are common in river floodplains, where mud deposited by a flood eventually dries out when the floodwaters recede. In rare cases, raindrop impressions are preserved on the bedding surfaces of mud that has dried out, although raindrop impressions are very delicate sedimentary structure that are rarely preserved. Much more common are grated beds, formed when a flow-carrying sediment slows down and the size of the sediment that is deposited decreases through time. That is, the grated bed has the coarsest clasts at its base and the finest clasts at its top. Grated beds can be produced by a flood that wanes through time. Grated beds also are very common in deep marine environments where turbulent mixtures of sediment and water called turbidity currents move downslope, coming to rest eventually as the current slows down and eventually stops. Such grated beds are called turbidites. Fossils and biogenic structures include remains and traces of plants or animals preserved in rock, any evidence of past life. Fossils include remains of shells, bones, or teeth, whole bodies preserved in mudstone, amber, or ice, and a variety of tracks, trails, and burrows that collectively are called trace fossils. Fossils are discussed further in Chapter 4. Metamorphic rocks. A potter forms a delicate vase from moist clay. She places the soft piece in a kiln and slowly heats it to 1000 degrees Celsius. As temperature rises, the clay minerals decompose. Atoms from the clay then recombine to form new minerals that make the vase strong and hard. The breakdown of the clay minerals, growth of new minerals, and hardening of the vase all occur without melting the solid materials. Metamorphism is the process by which rising temperature and pressure, or changing chemical conditions, transform rocks and minerals. Metamorphism occurs in solid rock, like the transformations in the vase as the potter fires it in her kiln. Small amounts of water and other fluids speed up the metamorphic mineral reactions, but the rock remains solid as it changes. Metamorphism can change any type of parent rock, sedimentary, igneous, or even another metamorphic rock. A mineral that does not decompose or change in other ways, no matter how much time passes, is a stable mineral. A stable mineral can become unstable when environmental conditions change. 3 types of environmental change affect mineral stability and cause metamorphism: rising temperature, rising pressure, and changing chemical composition. For example, when the potter put the clay in her kiln and raised the temperature, the clay minerals decomposed because they became unstable at the higher temperature. The atoms from the clay then recombined to form new minerals that were stable at the higher temperature. Similarly, if hot water seeping through bedrock carries new chemicals to a rock, those chemicals may react with the rock's original minerals to form different minerals that are stable in the new chemical environment. Thus, metamorphism occurs because each mineral is stable only within a certain range of temperature, pressure, and chemical environment. If temperature or pressure rises above that range, or if chemicals are added or removed from the rock's original minerals may decompose and their components recombine to form new minerals that are stable under the new conditions. Metamorphic grade. The metamorphic grade of a rock is the intensity of metamorphism that formed it. Temperature is the most important factor in metamorphism, and therefore, grade closely reflects the temperature of metamorphism. Because temperature increases with depth in Earth, a general relationship exists between depth and metamorphic grade. Low-grade metamorphism occurs at shallow depths, less than 10 kilometers beneath the surface, where temperature is no higher than 300 degrees Celsius to 400 degrees Celsius. Medium-grade conditions, where temperatures are between 400 degrees Celsius and 600 degrees Celsius, exist at depths between about 10 and 40 kilometers. High-grade conditions are found deep within the continental crust and in the upper mantle, 40 to 55 kilometers below Earth's surface. The temperature there is 600 degrees Celsius to 800 degrees Celsius, close to the melting point of rock. High-grade conditions can develop at shallower depths, however, in rocks adjacent to hot magma. For example, today, metamorphic rocks are forming beneath Yellowstone Park, where hot magma lies close to Earth's surface. Metamorphic changes. Metamorphism commonly alters both the texture and mineral content of a rock. Textural changes as a rock undergoes metamorphism. Some mineral grains grow larger and others shrink. The shapes of the grains may also change. For example, the fossiliferous limestone shown in Figure 3.23a is a sedimentary rock, but if it is subject to high temperature and pressure, the small calcite crystals that make up both the fossils and the cement between them will recrystallize, with some crystals growing at the expense of others. In the process, the fossils will be slowly destroyed and the rock will transform into marble, a metamorphic rock composed of calcite but with a texture consisting instead of large, interlocking crystals. Micas are common metamorphic minerals that form when many different parent rocks undergo metamorphism. Micas are shaped like pie plates. When metamorphism occurs, shape, the micas grow with random orientations, like pie plates flying through the air. However, when tectonic force squeezes rocks as they are heated during metamorphism, the rock deforms into folds. When rocks are folded as mica crystals are growing, the micas grow with their flat surfaces perpendicular to the direction of the squeezing. This parallel alignment of micas produces the metamorphic layering called foliation. The foliation layers can range in thickness from a fraction of a millimeter to a meter or more. Metamorphic rocks commonly will break parallel to foliation planes to form slaty cleavage. Although metamorphic foliation and the slaty cleavage that results can resemble sedimentary bedding, the two types of layering are different in origin. Foliation results from the alignment and segregation of metamorphic minerals during metamorphism. It forms at right angles to the direction of maximum compressive stress acting on the rocks. Stratification develops because sediments are deposited layer by layer. Mineralogical changes sometimes, when a parent rock contains only one mineral, metamorphism transforms the rock into one composed of the same mineral but with a coarser texture. Limestone converting to marble is one example of this generalization. Both rocks consist of the mineral calcite, but their respective textures are very different. Another example is the metamorphism of quartz sandstone to quartzite, a rock composed of recrystallized quartz grains. In contrast, metamorphism of a parent rock containing several minerals usually forms a rock with new and different minerals and a new texture. For example, a typical sedimentary mudstone contains large amounts of clay as well as quartz feldspar and several other minerals. When heated, some of those minerals decompose, and their atoms recombine to form new minerals such as mica, garnet, and a different kind of feldspar. Figure 3.38b shows a rock called gneiss that was formed when metamorphism altered both the texture and the minerals of mudstone. If migrating fluids alter the chemical composition of a rock, new minerals invariably form. Types of metamorphism and metamorphic rocks recall that rising temperature, rising pressure, and changing chemical environment cause metamorphism. In addition, deformation resulting from the movement of Earth's crust causes foliation to develop and thus strongly affects the texture of a metamorphic rock. Four different geologic processes create these changes. Contact metamorphism. Contact metamorphism occurs where hot magma intrudes cooler rock of any type, sedimentary, metamorphic, or igneous. The highest grade metamorphic rocks form at the contact point, closest to the magma. Lower grade rocks develop farther away. A metamorphic halo around a pluton can range in width from less than a meter to hundreds of meters, depending on the size and temperature of the intrusion and the effects of water or other fluids. Contact metamorphism commonly occurs without deformation. As a result, the metamorphic minerals grow with random orientations, like the pie plates flying through the air, and the rocks develop no foliation. The rock hornfels is a common unfoliated metamorphic rock that forms by contact metamorphism of mudstone. Burial metamorphism. Burial metamorphism results from the burial of rocks in a sedimentary basin. Younger sediment may bury the oldest layers to depths greater than 10 kilometers in a large basin. Over time, temperature and pressure increase within the deeper layers until burial metamorphism begins. Burial metamorphism is occurring today in the sediments underlying many large deltas, including the Mississippi River Delta, the Amazon Basin on the east coast of South America, and the Niger River Delta on the west coast of Africa. Like contact metamorphism, burial metamorphism occurs without deformation. Consequently, metamorphic minerals grow with random orientations and, like contact metamorphic rocks, burial metamorphic rocks are unfoliated. Regional dynamothermal metamorphism. Regional dynamothermal metamorphism occurs where major crustal movements build mountains and deform rocks. The term dynamothermal simply indicates that the rocks are being deformed and heated at the same time. It is the most common and widespread type of metamorphism and affects broad regions of Earth's crust. Magma rises and heats large portions of the crust in places where tectonic plates converge. The high temperatures cause new metamorphic minerals to form throughout the region. The rising magma also deforms the hot, plastic country rock as it forces its way upward. At the same time, the movements of the crust squeeze and deform rocks. As a result of all these processes acting together, regionally metamorphosed rocks are strongly foliated and are typically associated with mountains and igneous rocks. Regional dynamothermal metamorphism produces zones of foliated metamorphic rocks tens to hundreds of kilometers across. For example, large portions of the Appalachian Mountains in the eastern United States have undergone dynamothermal metamorphism and exhibit well-developed foliation. Among the best examples of the changes in texture and mineral content that accompany metamorphism are those that occur in mudstone with increasing metamorphic grade. The most abundant type of sedimentary rock, mudstone, consists mainly of clay minerals, quartz, and feldspar. The mineral grains are too small to be seen with the unaided eye. As regional metamorphism begins, clay minerals break down and mica and chlorite replace them. These new, platy minerals grow perpendicular to the direction of squeezing. As a result, the rock develops slaty cleavage and is called slate. With rising temperature and continued deformation, the micas and chlorite grow larger, and wavy or wrinkled surfaces replace the flat slaty cleavage, creating phyllite, which has a glossy appearance compared to slate, which is more dull. In both slate and phyllite, the mica and chlorite are too small to be seen with the unaided eye. As the temperature continues to rise, the mica and chlorite grow large enough to be seen without a microscope and foliation becomes very well developed. Rock of this type is called schist. Schist forms approximately at the transition from low to intermediate metamorphic grades. At high metamorphic grades, light and dark-colored minerals often separate into bands that are thicker than the layers of schist, to form a rock called gneiss. At the highest metamorphic grade, the rock begins to melt, though only partially, forming small veins of granitic magma. When metamorphism wanes and the rock cools, the magma veins solidify to form migmatite, a mixture of igneous and metamorphic rock. Hydrothermal metamorphism water is a chemically active fluid. It attacks and dissolves rocks and minerals. If the water is hot, it attacks minerals even more rapidly. Hydrothermal metamorphism occurs when hot water and ions dissolved in the hot water react with a rock to change its chemical composition and minerals. Most rocks and magma contain very low concentrations of metals such as gold, silver, copper, lead, and zinc. For example, gold makes up 0.000002% of average crustal rock, while copper makes up 0.0058% and lead comprises 0.0001%. Although the metals are present in very low concentrations, hydrothermal solutions sweep slowly through large volumes of country rock, dissolving and accumulating the metals as they go. The solutions then deposit the dissolved metals where they encounter changes in temperature, pressure, or chemical environment. In this way, hydrothermal solutions scavenge and concentrate metals from average crustal rocks and then deposit them locally to form ore. Hydrothermal ore deposits are discussed further in Chapter 5. Chapter 4, Geologic Time. Earth rocks, Earth history, and mass extinctions in many locations across Europe and later in North America. 19th-century geologists found thick sequences of sedimentary rock layers containing abundant fossil organisms preserved in them. The geologists also found layers of rock containing few or no fossils lying above the fossil-rich rocks. Even higher in the sequence of rock layers, they found fossils again, but of organisms very different from those in the older rocks. Most surprising, many of the most abundant fossilized organisms in lower layers never appeared again in the younger rocks. Those organisms simply had disappeared from the surface of Earth forever, as though suddenly extinguished, never to return. Today, we know through this fossil record that more than once, a sudden, catastrophic event has abruptly decimated life on Earth, causing a mass extinction in which many types of organisms simply were wiped out. Following each extinction event, new life forms slowly emerged and these new life forms recolonized the planet. The idea that life on Earth underwent catastrophic extinctions due to geologic events that affected the entire planet was not accepted by many geologists of the 20th century. Instead, they suggested that perhaps the rocks containing evidence of more gradual changes in Earth's lifeforms simply had been destroyed by erosion or were never deposited. According to this reasoning, evidence for the gradual decline of species that became extinct and the slow emergence of new species simply was missing from the rock record or had not been found. Following the conventional wisdom of the time, scientists concluded that the extinctions of old life forms and the emergence of new ones occurred slowly, as a result of gradually changing conditions. As travel became easier in the 20th century and more of Earth's rock record could be reached and studied by scientists, many searched for fossiliferous rocks of the appropriate ages to fill in the gaps and provide evidence for gradual extinctions, but these rocks were never found. Instead, the scientists found an abundance of geologic evidence indicating that the near-instantaneous mass extinctions occurred at least 5 times in the geologic past, each time decimating life on Earth as it existed at that time. The most dramatic extinction occurred about 252 million years ago, at the end of the Permian period. At that time, 90% of all species in the oceans suddenly died out. On land, about 2/3 of reptile and amphibian species and 30% of insect species also vanished. In his book describing this extinction, author Douglas Irwin exclaims that it was, "the closest life has come to complete extermination since its origin." The death of most life forms at the end of the Permian period left huge ecological voids in the biosphere. Ocean ecosystems changed as new organisms emerged in an environment relatively free of predators and competition. On land, terrestrial animals including dinosaurs slowly appeared and proliferated. Plants too underwent major changes that led to the evolution of the first flowering plants. About 65 million years ago, at the end of the Cretaceous period, another catastrophic extinction wiped out up to 50% of Earth's genera, including the dinosaurs. Small mammals survived this disaster, facing a new world free of the efficient predators that had hunted them. Grasses also evolved after the Cretaceous extinction event, leading to the establishment of widespread grasslands ecosystems. Eventually, humans evolved. What kinds of catastrophic events caused these sudden extinctions? Why would species that had survived for tens of millions of years or more disappear so rapidly? Here we consider 3 hypotheses for mass extinctions. Each of these hypotheses involves large-scale interactions among Earth's 4 major systems. The geosphere, atmosphere, hydrosphere, and biosphere all were involved in each type of mass extinction. The trigger that initiated the radical changes among the 4 Earth systems and caused the mass extinction is the main difference between each hypothesis. Extraterrestrial impacts in the late 1970s, the father and son team of Walter and Luis Alvarez were studying sedimentary rocks deposited when the dinosaurs and so many other life forms were becoming extinct. In one layer, they found abundant dinosaur fossils. Just above it, they found very few fossils of any kind and no dinosaur fossils. Between these 2 rock layers they found a thin, sooty layer of clay. They brought samples of the clay to the laboratory and found that it contained high concentrations of the element iridium. This discovery was surprising because iridium is rare in Earth rocks. Where did it come from? Although rare in Earth's crust, iridium is more abundant in meteorites. In a landmark paper published in 1980, Walter and Luis Alvarez suggested that 65 million years ago, a meteorite roughly 10 kilometers in diameter hit the Earth with explosive energy many thousands of times greater than that of today's entire global nuclear arsenal. The collision vaporized both the meteorite and Earth's crust at the point of impact, forming a plume of hot dust and gas that rose into the upper atmosphere and circled the globe. This thick, dark cloud blotted out the sun, significantly reducing the amount of solar energy that reached Earth's surface for up to several years. Particularly hard hit were microscopic algae and other tiny photosynthesizing organisms in the oceans that were unable to survive under the reduced levels of solar energy reaching the surface. The widespread die-off of photosynthesizing organisms in the oceans greatly reduced the base of the food chain and contributed to the extinction of larger marine organisms such as ammonites and plesiosaurs, a kind of swimming dinosaur. The reduced solar energy reaching the surface also resulted in less vegetation, ultimately eliminating all dinosaurs and many reptiles. Analysis of the fossil record has suggested that nothing with a body mass exceeding 25 kilograms survived. The now famous 1980 paper by the Alvarez team created a considerable stir among geologists, in part because the paper cited compelling evidence for the impact but did not identify the actual impact site. At about the same time, geophysicist Glenn Penfield was analyzing magnetic surveys of the Yucatan Peninsula for the Mexican oil company Pemex, when he discovered the presence of a large, symmetrical semicircle in the Gulf of Mexico on the northwest side of the peninsula. Obtaining data from an older gravity survey of the peninsula, Penfield noticed that a second semicircle was present on shore and that the two semicircles together formed a large, circular structure about 70 kilometers across. Although Penfield and his co-workers suspected that the circular structure might be the missing impact site, they were not able to secure any rock samples from the area to examine for evidence of an impact, and Pemex did not allow them to publish the geophysical data behind their discovery. Instead, they published a short abstract and presented a brief talk in 1981, announcing the discovery of a large igneous body in the Yucatan Peninsula. It was not until 1991, 14 years after the Alvarez paper, that a team of scientists had amassed sufficient data, including rock samples from old Pemex oil wells in the area, to publish the first paper describing the site as an impact structure. Since then, many analyses of the impact site and surrounding areas have suggested that it occurred 65 million years ago, coinciding with the Cretaceous extinction event. Although much evidence in support of the Yucatan site as a major impact structure has been published since 1991, its relation to the mass extinction at the end of the Cretaceous period is still the subject of vigorous debate. Careful analyses of fossils preserved in sediment cores recovered from the crater have indicated that the impact actually occurred about 300,000 years prior to the extinction event. In addition, other possible large impact sites of late Cretaceous age have been described in the North Sea, the Ukraine, and India. At the latter location, an impact crater more than 500 kilometers in diameter, the biggest on Earth, has been reported. Although the Yucatan impact site was hailed for many years as the smoking gun that caused the Cretaceous terminal extinction event, these more recent findings cast doubt on that simple explanation. Some scientists have suggested that widespread volcanism in India, combined with severe greenhouse conditions at the end of the Cretaceous, caused significant environmental stress that reduced the population sizes of many species prior to the Yucatan impact. These scientists have suggested that the impact itself did not catastrophically kill a healthy, thriving biosphere, but rather pushed an already very stressed biosphere over the threshold that led to a major extinction. Although the extraterrestrial impact hypothesis still is very popular overall, reports of other major impact sites of late Cretaceous age and uncertainty about the role that factors such as volcanism may have played will keep scientific interest fixed for the foreseeable future on the cause of the Cretaceous extinction event. Volcanic eruptions. A volcanic eruption ejects gas and fine ash into the atmosphere. The volcanic ash serves like an umbrella that reflects sunlight back into space and thus causes climate to cool. 1. Volcanic gas. Sulfur dioxide forms small particles called aerosols that also reflect sunlight and cool Earth. Carbon dioxide is another gas emitted by volcanoes. It is a greenhouse gas that can cause warming of Earth's atmosphere. Thus, volcanoes erupt materials capable of causing both atmospheric cooling and warming. In many eruptions, the cooling overwhelms the warming effects. This cooling can occur rapidly, within a few weeks or months of the eruption. Scientists have noted that some mass extinctions coincided with unusually high rates of volcanic activity. For example, massive flood basalts erupted onto Earth's surface in Siberia roughly 252 million years ago, at the same time that the Permian extinction occurred. According to one hypothesis, explosive volcanic eruptions blasted massive amounts of volcanic ash and sulfur aerosols into the air. The ash and aerosols spread like a pall throughout the upper atmosphere, blocking out the sun. Earth's atmospheric and oceanic temperatures plummeted, plants withered, and animals starved or froze to death. If this hypothesis is correct, the Permian extinction resulted from a classic Earth systems interaction, in which a volcanic eruption occurring within the geosphere altered the composition of the atmosphere, with profound consequences for atmospheric and marine temperatures, and for life. Supercontinents and Earth's carbon dioxide budget in modern oceans. Cold polar seawater sinks to the seafloor and flows as a deep ocean current toward the equator. This current transports oxygen to the deep ocean basins and forces the deep water to rise near the equator, where it is warmed. The current thus mixes both heat and gases throughout the oceans and the atmosphere. Surface marine organisms that photosynthesize absorb atmospheric carbon dioxide and use it to produce organic tissue. These organisms then die and settle to the seafloor, thereby removing carbon from the atmosphere and transporting it to the seafloor. Some of the carbon converts back to carbon dioxide as organisms living in the deeper ocean water consume the settling organic matter, and some of this carbon dioxide is returned to the atmosphere as modern ocean currents mix the deep and shallow seawater. Ocean currents are partially controlled by the positions of the continents. Recall from Chapter 1 that the continents slowly drift around the globe. Several times in Earth history, all the continents have joined together to form one giant supercontinent. One such supercontinent, called Pangaea, assembled during Permian time. The growth of Pangaea also caused a single global ocean to be formed. Computer models and the rock record both suggest that the assembly of all continents into a single landmass and the development of a single global ocean largely prevented mixing of the surface water and the ocean depths during Permian time. The lack of vertical mixing caused the chemistry of the ocean water to change drastically. As ocean water stagnated, two major changes in water chemistry began to take place in some parts of the Permian Ocean. First, Permian seawater lost most or all of its dissolved oxygen as organic matter that washed in from the continents or from dead planktons from the surface waters sank and were decomposed by oxidizing bacteria. Oxidizing bacteria require oxygen to decompose organic matter, so eventually the available oxygen was used up, resulting in a condition called anoxia, no measurable dissolved oxygen. Once the oxygen was gone and the oxidizing bacteria with it, sulfate-reducing bacteria took over and continued to decompose the available organic matter. Sulfate-reducing bacteria convert sulfate dissolved in the seawater to sulfide in order to obtain energy for growth. This conversion produces the byproduct hydrogen sulfide, a colorless, poisonous gas. In some parts of the Permian Ocean, not only was most or all of the dissolved oxygen removed, but the water became so full of dissolved hydrogen sulfide that it began to come out of solution and form tiny bubbles, a condition known as euxemia. The anoxic, euxinic conditions that developed in some parts of the Permian Ocean were deadly to nearly all species of metacellular marine life living near or on the seafloor. Organisms living near the surface were less affected because oxygen from the atmosphere could still mix with the water from wave energy to keep the water chemistry at the surface from becoming anoxic. Some surface planktons were able to thrive and in so doing continued to remove carbon dioxide from the atmosphere and supply organic carbon to the bottom waters which remained anoxic and euxinic. Removal of carbon dioxide from the atmosphere caused a decrease in greenhouse warming and resulted in global cooling. Some scientists have suggested that this global cooling led directly to the formation of continental ice sheets. When water cools, it becomes denser. The late Permian global cooling eventually reached a threshold at which polar surface water became denser than the deep water. At this point, the cool, dense surface water sank, displacing the carbon dioxide, rich deep water and causing it to rise toward the sea surface, where massive amounts of carbon dioxide were released into the atmosphere. According to this hypothesis, the high levels of atmospheric carbon dioxide asphyxiated much life both in the seas and on the continents and caused the Permian extinction event. Later, new organisms evolved when the carbon dioxide levels fell. Geologic time. While most of us think of time in terms of days or years, Earth scientists commonly refer to events that happened millions or billions of years ago. In Chapter 1 you learned that Earth is approximately 4.6 billion years old. Yet humans and our human-like ancestors have existed for only 5 to 7 million years, and recorded history is only a few thousand years old. How do scientists measure the ages of rocks and events that occurred millions or billions of years ago, long before recorded history or even human existence? Scientists measure geologic time in two ways. Relative age determination refers only to the order in which events occurred and is based on a few simple principles. For example, in order for an event to affect a rock, the rock must exist first. Thus, the rock must be older than the event. This principle seems obvious, yet it is the basis of much geologic work. As you learned in Chapter 3, sediment normally accumulates in horizontal layers. However, the sedimentary rocks in Figure 4.5 are folded and tilted. We deduce that the folding and tilting occurred after the sediment accumulated. The order in which rocks and geologic features formed can usually be interpreted by such observation and logic. Absolute age is age in numeric years. For example, the dinosaurs became extinct about 66 million years ago. The Permian extinction occurred 252 million years ago. The last catastrophic eruption of the Yellowstone volcano occurred 630,000 years ago. Absolute age tells us both the order in which events occurred and the amount of time that has passed since they occurred. Relative geologic time absolute age measurements have become common only since the second half of the 20th century. Prior to that time, geologists used field observations to determine relative ages. Even with today's sophisticated laboratory instrumentation, most field geologists routinely make relative age determinations based on the following simple principles. The principle of original horizontality is based on the observation that sediment usually accumulates in horizontal layers. If sedimentary rocks lie at an angle, as in Figure 4.6b, or if they are folded as you saw in Figure 4.5, we can infer that tectonic forces tilted or folded them after they formed. The principle of superposition states that in an undeformed sequence of layered sedimentary rocks, the oldest layers are at the bottom and the youngest layers are at the top. For example, in Figure 4.7, the sedimentary layers become progressively younger in the order 1, 2, 3, 4, and 5. Two notable exceptions to this principle occur if tectonic forces have turned the layers of sedimentary rock upside down or have caused an older layer to be shoved up and over a younger layer. The principle of cross-cutting relationships is based on the obvious fact that a rock must first exist before anything can happen to it. Figure 4.8 shows an igneous intrusion, called a dike, cutting across conglomerate. Clearly, the dike must be younger than the conglomerate. Figure 4.9 shows sedimentary rocks intruded by three granite dikes. Dike 2 cuts dike 1, and dike 3 cuts dike 2, so 2 is younger than 1, and 3 is the youngest. The sedimentary rocks must be older than all the dikes. A similarly obvious fact is that a rock must first exist before pieces of it can be broken off and incorporated into another geologic unit. Hence, the principle of included fragments requires that a conglomerate that contains clasts of granite must be younger than the age of the granite. Similarly, pieces of sandstone incorporated into a basalt flow must be older than the flow. The theory of evolution states that life forms have changed throughout geologic time. Species emerge, persist for a while, and then become extinct. Recall from Chapter 3 that fossils consist of the remains and other traces of prehistoric life preserved in sedimentary rocks. Fossils are useful in determining relative ages of rocks, because different animals and plants lived at different times in Earth history. For example, trilobites lived from about 521 million to about 252 million years ago, and the first dinosaurs appeared about 240 million years ago. The principle of superposition tells us that sedimentary rock layers become younger from bottom to top. If the rocks formed over a long time, different fossils appear and then vanish from bottom to top, in the same order in which the organisms evolved and then became extinct. Rocks containing dinosaur bones must be younger than those containing trilobite remains. The principle of faunal succession states that species succeeded one another through time in a definite and recognizable order, and that the relative ages of sedimentary rocks can therefore be recognized from their fossils. For example, a layer of sedimentary rock containing trilobite fossils will always be older than a layer of sedimentary rock with dinosaur bones, because trilobites Evolved and went extinct before the dinosaurs evolved. Figure 4.12. Interpreting geologic history from fossils. Paleontologists study fossils to understand the history of life and evolution. The oldest known fossils are traces of bacteria-like organisms that lived about 3.5 billion years ago. A much younger fossil consists of the frozen and mummified remains of a Bronze Age man, recently found in a glacier near the Italian-Austrian border. Fossils also allow geologists to interpret ancient environments, because most organisms thrive in specific environments and do not survive in others. For example, all modern species of coral live in marine environments. Corals do not survive in fresh or even brackish water. Yet today, fossil corals are abundant in the rocks of many mountain environments, including the Canadian Rockies, the European Alps, and the Tian Shan of western China. Each of these mountain ranges are hundreds of kilometers or more away from the nearest ocean. The fossil corals tell us that the rocks exposed in these mountains were once submerged beneath marine waters. Today, geologists understand that tectonic processes raised the marine rocks and their fossils to their present altitudes. Although some individual fossils can be used to recognize ancient depositional environments, like corals representing a normal marine environment, geologists more often use the entire fossil assemblage in a rock formation to interpret its depositional environment. For example, if the collection of fossils in a rock sequence includes numerous different species of body fossils and a wide variety of trace fossils, geologists might infer that the environment was widely suitable for inhabitation. Shallow marine environments in tropical or temperate waters are such environments. The rich ecosystem supports a diversity of life forms. On the other hand, if only one or two fossil types occur in a sedimentary rock sequence and the trace fossil diversity also is low, geologists might infer that the environment of deposition was stressful and only a few types of specialized organisms could survive. Deserts represent such a hostile environment of deposition. Unconformities and correlation. The walls of the Grand Canyon are composed of sedimentary rocks lying on older igneous and metamorphic rocks. Their ages range from about 200 million years to nearly 2 billion years. The principle of superposition tells us that the deepest sedimentary rocks are the oldest, and the rocks become younger as we climb up the canyon walls. However, no principle assures us that the rocks formed continuously from 2 billion to 200 million years ago. The rock record may be incomplete. Suppose that no sediment was deposited for a period of time, or that erosion removed some sedimentary layers before younger layers accumulated. In either case, a gap would exist in the rock record. We know that in an undeformed layered sequence of sedimentary rock, any one layer is younger than the layer below it, but without more information we do not know how. Much younger, unconformities layers of sedimentary rocks are conformable if they were deposited without detectable interruption. An unconformity is a bounding surface that exists between two rock units and represents an interruption in deposition, usually of long duration. Some rock may have been eroded during the time frame represented by the unconformity, but eventually deposition of sediment resumed and buried the unconformity. Thus, an unconformity is a physical feature that represents a long interval of time for which no geologic record exists in that place. The missing record may involve billions of years. Several types of unconformities exist. In a disconformity, the sedimentary layers above and below the unconformity are parallel. Some disconformities are produced by downward or lateral erosion through previously deposited layers of sediment through the process of reworking. For example, river channels and deep-sea submarine channels both can erode downward and sideways through time, resulting in a disconformity that curves upward at the margins of the former channel. Although some disconformities, like the submarine channel example shown in Figure 4.15, are relatively easy to recognize in a good exposure of sedimentary rocks, many disconformities are much more subtle and difficult to recognize without detailed investigation of the rock texture, composition, sedimentary structures, and fossil content. For example, layers of sediment that accumulate slowly on parts of the seafloor can all consist of similar-looking mud. In such mud-rich sediment sequences, disconformities that may represent tens or hundreds of thousands of years can be very difficult to recognize without detailed study of the mud itself. Another example of a subtle disconformity is shown in Figure 4.16. In this case, the disconformity was formed by a break in deposition on a shallow marine sandbar. In some cases, disconformities can be identified by determining the ages of rocks, using methods based on fossils and absolute dating, described below. In an angular unconformity, tectonic activity tilted older sedimentary rock layers and erosion planed them off before the younger sediment accumulated. Although some disconformities involve the erosional truncation of underlying beds as shown in Figure 4.15, the erosion of the underlying beds was produced by lateral erosion in a former channel. The rocks under the disconformity were not tectonically tilted prior to their partial removal by erosion. Disconformities are architectural elements that contribute significantly to the three-dimensional shape of sediment layers in which they occur. In the case of a great cathedral or modern skyscraper, the architectural elements include the arrangement, size, and shape of a building support structure, framing, window placement, embellishments, and so on. Similarly, sedimentary architectural elements include the thickness and lateral dimensions of sediment beds, the 3D shape of disconformities within a sediment sequence, and the type and geometry of sedimentary structures present within the beds. The architectural elements exposed in ancient sequences of sedimentary rocks provide very useful information for geologists concerned with interpreting the depositional environments represented by the sedimentary deposits. A nonconformity is an unconformity in which sedimentary rocks lie on igneous or metamorphic rocks. The nonconformity shown in Figure 4.13 represents a time gap of about 1 billion years. Perhaps the best exposed and widespread example of a nonconformity is the unconformity that separates metamorphic and igneous rocks that make up the basement rocks of Earth's continents and the overlying sedimentary rocks that have been deposited on top of it. Because it is so widespread and represents such a significant break in the geologic record of the continents, this nonconformity commonly is called the Great Unconformity. Correlation. Ideally, geologists would like to develop a continuous history for each region of Earth by interpreting rocks that formed in that place throughout geologic time. However, there is no single place on Earth where rocks were continuously formed and preserved. Consequently, in any one place, the rock record, that is, the rocks that currently exist on Earth and contain the record of its history, is full of unconformities, or historical gaps. To assemble as complete and continuous a record as possible, geologists gather geological evidence from many localities and match rocks of the same age from different localities in a process called correlation. The correlation of rock of the same age over great distances is at the heart of reconstructing Earth's ancient systems and recognizing when and how these changes affected the surface of the Earth. Correlating rock sequences from one region on Earth to another is complicated by the great variety of environments that existed at any single time in Earth's geologic past, not to mention the massive changes that Earth's systems have undergone over the past 4.6 billion years since the planet first formed. In order to understand what even a small part of Earth's surface looked like at any point during the geologic past, geologists must be able to correlate rocks that formed in different environments that existed at the same point in time. Today, for example, the East Coast region of North America includes the Appalachian Mountains, a very gently sloping mostly flat coastal plain, the shoreline environment, and the shallow marine settings offshore ranging from the ankle-deep swash zone to the outer part of the continental shelf over 100 kilometers beyond the shoreline. Beyond the continental shelf are environments of the deeper ocean. Each of these environments is very different, yet all exist today, at this point in geologic time. Therefore, the primary aim of correlation is the recognition of time equivalence between different sequences of physical sedimentary rock. If you follow a single sedimentary bed from one place to another, then it is clearly the same layer in both places. It is natural to suppose that because the layer can be physically traced from one place to another that the layer therefore must be the same age everywhere. This supposition is almost never the case, however, and has misled geologists for many decades. Although a layer may be physically traced, the result does not reflect a set of environments that changed in space, but rather a set of environments that change in space and through time. For example, many rivers will migrate laterally over many decades or hundreds of years as one bank erodes and the opposite bank builds out. The result is a layer of sandstone that was not deposited all at once, but instead grew laterally as the river slowly migrated. In a larger scale example, suppose you are attempting to trace a layer of sandstone deposited by a beach. If the relative sea level rose and slowly inundated a continental interior, the beach would also migrate inland. However, those beach deposits closer to the edge of the continent would be older than the beach deposits further inland. Thus, although the entire layer would be physically continuous, it would not be the same age everywhere and therefore would not correlate in time. Over a few hundred meters, the age difference within the sandstone layer may be unimportant, but over hundreds of kilometers it could vary by millions of years. So there are two kinds of correlation. Time correlation refers to age equivalence, and lithologic correlation refers to the continuity of a rock unit. The two are not always the same, because some rock units, such as the sandstone, were deposited at different times in different places. To construct a record of Earth history and a geologic time scale, Earth scientists use several types of evidence to correlate rocks of the same age. Index fossils are a very useful tool for correlation, because they can precisely indicate the ages of sedimentary rocks. The best index fossils are abundantly preserved in rocks, are geographically widespread, existed as a species or genus for only a relatively short time, and are easily identified in the field. Floating or swimming tiny marine organisms make some of the best index fossils because they spread rapidly and widely throughout the seas and they evolved quickly. The shorter the time that a species existed, the more precisely the index fossil reflects the age of a rock. In many cases, the presence of a single type of index fossil is sufficient to establish the age of a rock. More commonly, an assemblage of several fossils is used to date and correlate rocks. For example, the exact position of the Cretaceous Tertiary boundary in the sediment core from the Yucatan meteor impact site, described above, was determined by using tiny floating marine organisms as index fossils. Another correlation tool is the key bed, a thin, widespread, easily recognized sedimentary layer that was deposited rapidly and simultaneously over a wide area. Many volcanic eruptions eject great volumes of fine, glassy volcanic ash into the atmosphere. Wind carries the ash over great distances before it settles. Some historic ash clouds have encircled the globe. When the ash settles, it forms a depositional layer, and the glassy fragments within the ash layer typically crystallize to form clay. Because such volcanic eruptions occur at a precise point in time, the ash deposit is the same age everywhere. Thus, the thin, sooty, iridium-rich clay layer deposited roughly 65 million years ago from debris of a giant meteorite impact is a classic example of a key bed. A more recent key bed is the thin layer of white volcanic ash shown in Figure 4.24 from western Montana. The layer of ash in the photo came from a massive eruption that occurred 11,200 years ago from Glacier Peak, an active volcano northeast of Seattle, Washington. Absolute geologic time geologists have a challenging task. They are attempting to measure the absolute age of events that occurred before history was recorded. Measuring absolute age relies on a process that occurs at a constant rate, such as Earth rotating once every 24 hours, and some way to keep a cumulative record of that process, such as marking a calendar each time the sun rises. Measurement of time with a calendar, a clock, an hourglass, or any other device depends on these two factors. Fortunately, scientists have found a natural process that occurs at a constant rate and accumulates its own record. It is the radioactive decay of elements that are present in many rocks. Thus, many rocks have built-in calendars. To begin to understand radioactivity, we need a basic understanding of the atom. An atom consists of a small, dense nucleus surrounded by a cloud of electrons. A nucleus consists of positively charged protons and neutral particles called neutrons. All atoms of any given element have the same number of protons in the nucleus. However, the number of neutrons may vary. Isotopes are atoms of the same element with different numbers of neutrons. For example, all isotopes of carbon contain 6 protons, but only carbon-12 also has 6 neutrons. Carbon-13 has 7 neutrons, and carbon-14 has 8 neutrons. Many isotopes are stable, meaning that they do not change with time. Carbon-12 is one such isotope. If you study a sample of carbon-12 for 1,000,000 years, all of the atoms would remain unchanged. However, other isotopes are unstable or radioactive. Given time, their nuclei spontaneously decay, forming a different isotope and commonly a different element. For example, carbon-14, the one unstable isotope of carbon, spontaneously decays to form nitrogen-14. A radioactive isotope such as carbon-14 is known as a parent isotope. An isotope created by radioactivity, such as nitrogen-14, is called a daughter isotope. Many common elements, including carbon and potassium, consist of a mixture of radioactive and non-radioactive isotopes. With time, the radioactive isotopes decay, but the non-radioactive ones do not. Some elements, such as uranium, consist only of radioactive isotopes. The amount of uranium on Earth slowly decreases as it decays to other elements, such as lead. Radioactivity and half-life. If you watch a single atom of carbon-14, when will it decompose? This question cannot be answered, because any particular carbon-14 atom may or may not decompose at any time. Each atom has a certain probability of decaying at any time. Averaged over time, half of the atoms in any sample of carbon-14 will decompose in 5,730 years. The half-life is the time it takes for half of the atoms in a radioactive sample to decompose. The half-life of carbon-14 is 5,730 years. Therefore, if 1 gram of carbon-14 were placed in a container, 0.5 gram would remain after 5,730 years, 0.25 gram after 11,460 years, and so on. Each radioactive isotope has its own half-life. Some half-lives are fractions of a second, and others are measured in billions of years. Radiometric dating too. Properties of radioactivity are essential to the calendars in rocks. First, the half-life of a radioactive isotope is constant. It can be measured in the laboratory and is unaffected by geologic or chemical processes, so radioactive decay occurs at a known, constant rate. Second, as a parent isotope decays, its daughter accumulates in the rock. The longer the rock exists, the more the daughter isotope accumulates. Radiometric dating is the process of determining the absolute ages of rocks, minerals, and fossils by measuring the relative amounts of parent and daughter isotopes. Figure 4.25 shows the relationships between age and relative amounts of parent and daughter isotopes. At the end of one half-life, 50% of the parent atoms have decayed to daughter. At the end of 2 half-lives, the mixture is 25% parent and 75% daughter. To determine the age of a rock, a geologist measures the proportions of parent and daughter isotopes in a sample and compares the ratio to a similar graph. Consider a hypothetical parent-daughter pair having a half-life of 1,000,000 years. If we determine that a rock contains a mixture of 25% parent isotope and 75% daughter, figure 4.19 shows that the age is 2 half-lives. Or in this case 2,000,000 years. If the half-life of a radioactive isotope is short, that isotope gives accurate ages for young materials. For example, the half-life of 5,730 years for carbon-14 dating allows age determinations for materials younger than about 50,000 years. It is useless for older materials, because by 50,000 years, the amount of carbon-14 that remains in the sample is too small to measure accurately. The opposite limitation exists for isotopes with long half-lives. Such isotopes provide accurate ages for old rocks, but not enough daughter accumulates in young rocks to be measured. For example, rubidium-87 has a half-life of 47 billion years. In a geologically short period of time, 10 million years or less, so little of its daughter has accumulated that it is impossible to measure accurately. Therefore, rubidium-87 is not useful for rocks younger than about 10 million years. The radioactive isotopes that are most commonly used for dating are summarized in Table 4.1. Advances in absolute age dating and their application to slowly unraveling Earth's history have undergone a renaissance over the past quarter century or so, as technology in general has advanced. Today, for example, it is possible to determine with accuracy and precision the age of individual grains of sand collected from an ancient sandstone. By isolating datable mineral grains, most commonly the mineral zircon, from a sandstone sample, geologists can measure the age of each grain, forming an age spectrum, a histogram of ages from all the individual grains measured. The age spectrum tells geologists the ages of rock that was eroded to form the sandstone. Along with information about the composition of the grains, that is, what types of minerals and rock fragments are represented, age spectra provide a direct link to the provenance of the sample. In addition, by applying the principle of included fragments to ages determined from individual grains of sand from an ancient sandstone, geologists are able to determine the maximum depositional age of the layer of sandstone from which the grains came. The grains must first have existed before they were eroded, transported, and deposited in the layer of sandstone that was collected by the geologist for analysis. Sequence stratigraphy, interpreting the rock record through time geology, is both an analytic and historic science. That is, geology uses the principles established by physicists and chemists to analyze the rock record systematically, but unlike the timeless principles upon which analytic science is based, such as Newton's law of gravitation, the evolution of Earth has taken place along a one-way timeline. Time has a direction, and insofar as understanding the ancient history of the Earth is concerned, geology events are bound by time. Earth history relies on a one-way record of physical remains left behind through the vast passage of geologic of time. This so-called rock record is very fragmented, because erosion has removed many older rock bodies that had formed during earlier phases of Earth's history. Nevertheless, the rock record was produced through time that travels in one direction. Ultimately, understanding and accurately reconstructing Earth's history relies on the ability of humans to place the physical evidence that is left behind into a temporal framework. In many geologic applications, relative age dating is sufficient to reconstruct the geologic events that transpired. However, the precision and accuracy with which geologists can determine the absolute age of geological events is among the biggest hurdles in reconstructing Earth history. For over 150 years, geologists used fossils to determine the age of sedimentary rocks. One of the earliest scientists to recognize that fossils in the rock record were related to time was the Frenchman Georges Cuvier. By reassembling the bones of fossil vertebrate organisms that had been unearthed from ancient rock or sediment, Cuvier was able to demonstrate convincingly to his contemporaries that many types of large vertebrates no longer exist today and therefore must have gone extinct. Cuvier assembled and described the first plesiosaur from a set of bones collected in England. He recognized that different types of teeth found in Ohio and transported back to Europe belonged to an extinct form of elephant-like creature, known as the mammoth. By the end of his career, Cuvier had reassembled the skeletons from and described dozens of now extinct organisms. Cuvier's work influenced a now famous scientist of the 1800s, Charles Darwin. In 1831, Darwin left his home in England for a sailing journey that took him around the world. His main goal was to describe the modern plants, animals, and environments that he encountered along the way, and in this sense was very much a sort of a natural scientist explorer. When he arrived in the Galapagos Islands, west of modern-day Ecuador, Darwin discovered that each island had its own unique species of finch, each with a particular set of adaptations not found anywhere else. Darwin reasoned that because the islands were physically separated by enough space, it prevented finches from island hopping, and that, through time, finch species on each island evolved independently through the process of natural selection. Natural selection, Darwin's most famous contribution to science, posits that as Earth environments change, individual species will change with it so as to be better adapted to the new environmental conditions. Those individuals with the specific trait needed to adapt to the new conditions would be stronger than those individuals without it and therefore more likely to have offspring. In this manner, the favorable trait would be preferentially passed down to future generations. Those species which developed the key trait are naturally selected to survive. Those species which did not, go extinct. Through the early works of Cuvier, Darwin, and others, scientists of the 1800s began to realize that many fossil organisms evolved through time and went extinct. Dinosaurs evolved and now are extinct, for example. Moreover, dinosaur remains are only found in rock layers of a specific age. By utilizing observations such as this, and by making detailed catalogs of the specific fossils that occurred across different sedimentary layers at a single locality, geologists quickly recognized that the fossils themselves provided an indication of the age of the rock. Through much of the late 1800s and early 1900s, thousands of paleontologists spent their careers studying, describing, and cataloging the detailed assemblage of fossils in rock sequences around the world. Not only were the bones of fossil vertebrates studied, but invertebrate fossils were widely collected and studied, as were tiny fossils called microfossils such as foraminifera or radiolaria, two types of single-celled protists with tiny shells that commonly are fossilized. As a result of the vast body of scientific literature that resulted from the many decades of detailed paleontologic study of Earth's fossil record, geologists developed the ability to recognize the age of a rock unit by the fossils it contains. In fact, for well over a century, fossils were used to subdivide and correlate rock units across the globe. By the mid-20th century, however, it became clear through detailed work that fossil occurrence relied not only on time but also on environment. As environments changed through time in one place, some fossil organisms simply migrated to another place. As a result, the age of many fossils was not the same everywhere. The age could vary laterally as organisms moved around. This realization contradicted the long-held assumption that fossil occurrence is strictly dependent on time. Instead of correlating beds containing the same fossils, a technique called biostratigraphy, or correlating rocks of similar lithology, called lithostratigraphy, today geologists correlate geologic deposits based on their age, or chronology, of deposition, that is, their chronostratigraphy. The key challenge in this regard is figuring out how to determine which rocks are time correlative, if neither fossils nor simple tracing of rock layers actually quite work for this purpose. The answer to this challenge developed in North America, as geologists studied the sedimentary layers across the continent and began to use modern geophysical tools to provide direct images of the large-scale architectural elements of sedimentary rocks in the subsurface. Early workers of North American stratigraphy began to notice that across the continent, unconformities occurred during certain periods of time and that no rock of these periods was preserved anywhere. The unconformities appeared to represent long periods of erosion or non-deposition, either one of which produces an unconformity. The same workers also noticed that for other long periods of time, sediments containing marine fossils were deposited most or all the way across the continent, unlike today. One of the first geologists to describe these widespread unconformities and the bodies of rock in between was Larry Sloss, a professor of geology at Northwestern University in Chicago from 1947 to his death in 1996. By carefully cataloging the type and ages of sedimentary rocks at different locations across North America, Sloss determined that the widespread unconformities subdivided the rock record into these unconformity-bound sequences from the European fossil-based geologic timescale. Sloss named each sequence after a tribe of North American natives in whose traditional homeland sedimentary rocks of the appropriate age were widespread. For example, he named the Sauk sequence after a tribe in Wisconsin where rocks belonging to the sequence are widely exposed. Figure 4.27 shows the Sauk sequence and Lower Tippecanoe sequence as mapped by Sloss along 4 separate lines of cross-sections in North America. After publishing his initial ideas about North American stratigraphic sequences, Sloss began compiling the records of Phanerozoic sedimentary rocks across Eurasia in order to see whether the ages of the major sequences corresponded to those from North America. In many cases, similar sequences could be identified across Eurasia and North America, although the exact timing of the beginning and end of each sequence and the size of each sequence, how much of the continent each sequence covered, varied somewhat. In the late 1960s, 3 of SLOS's graduate students were studying a set of sedimentary rocks in the mid-continent in which the different layers passed back and forth between those containing marine fossils and those containing land-dwelling fossils. Along with SLOS, the 3 students, Peter Vail, Robert Mitchum, and John Sangree, began to develop the idea that the rock layers were deposited as sea level fluctuated globally enough so that sometimes the continent was covered by marine water and sediment containing marine fossils was deposited, and other times the region was a terrestrial landscape with rivers and forests. They reasoned that a series of glacial intervals, commonly called ice ages, caused global sea level to fluctuate during the time the sediments were deposited. When ice built up during a glacial interval, sea level dropped and the North American continent was exposed. When ice melted between glacial intervals, sea level rose high enough to inundate the continents, creating marine environments with marine organisms. After their graduate work, Vail, Mitchum, and Sangree went to work at the research lab at Exxon, and there they had access to a huge volume of geologic information from the subsurface. They quickly adopted their techniques for separating rock units into unconformity-bounded sequences to the subsurface data they studied at Exxon. They recognized similar successions of rock sequences and unconformities on the margins of different continents, implying that global sea level did indeed rise and fall synchronously, and in so doing controlled the depositional environments left behind in the rock record. Over time, the concepts and techniques developed by the Exxon team became known as sequence stratigraphy, which is the framework most widely used today to correlate rock units and understand how the depositional environments those rock units reflect changed both through space and time. To understand how sequence stratigraphy works, consider the position of the shoreline. If sea level somehow rises, the shoreline will move landward. If sea level falls, the shoreline will move seaward. As the shoreline moves, all the depositional environments associated with the nearshore region also will migrate. For example, terrestrial environments will transform through time into marine environments as sea level inundates a particular location. Conversely, many formerly marine and nearshore environments become exposed and eroded as the shoreline recedes toward the ocean and river processes become important. Sequence stratigraphy, then, is the organization of sedimentary rock bodies into depositional units that are bounded by unconformities and that contain a set of key stratigraphic surfaces, each of which represents a single point in time. For example, if sea level rises to a maximum position, then begins to fall again, it will leave behind a recognizable change that is expressed as a single bedding surface developed at that point in time. By tracing this bedding surface from locality to locality, geologists are able to use it as a timeline for subdividing the sequence of rock above and below the surface. By recognizing bedding surfaces that correspond to different positions of the shoreline through time, geologists are able to erect a chronostratigraphic framework for the analysis of the sedimentary rock record. Figure 4.28 shows a cross-section of sedimentary rocks as they might occur over hundreds of kilometers, with different sequences of rock separated by unconformities. The lower panel in Figure 4.28 shows the same set of rocks recast into a chronostratigraphic framework through sequence stratigraphy. The geologic time scale. As mentioned earlier, no single locality exists on Earth where a complete sequence of rocks formed continuously throughout geologic time. However, geologists have analyzed and correlated rocks from many localities around the world to create the geologic time scale, a formal subdivision of Earth time based on numerical dates. The geologic time scale is frequently revised as more rock units are dated radiometrically and more fossil assemblages are described around the world. Just as a year is subdivided into months, months into weeks, and weeks into days, geologic time is split into smaller intervals. The units are named, just as months and days are. The largest time units are eons, which are divided into eras. Eras are subdivided, in turn, into periods, which are further subdivided into epochs and, even further, into ages. The geologic time scale was originally constructed on the basis of relative age determinations. When geologists developed radiometric dating, they added absolute ages to the time scale. Geologists commonly use the time scale to date rocks in the field. Imagine that you are studying sedimentary rocks in the walls of the Grand Canyon. If you find an index fossil or a key bed that has already been radiometrically dated by other scientists, you know the age of the rock you are studying and you do not need to send the sample to a laboratory for radiometric dating. The earliest eons of geologic time, Precambrian time. The earliest eons, the Hadean, Archean, and Proterozoic eons, often are not subdivided at all, even though together they constitute a time interval of 4 billion years, nearly 90% of Earth's history. These early eons are commonly referred to with the informal term Precambrian, because they preceded the Cambrian period, when fossil remains became very abundant. The Hadean eon is the earliest time in Earth history and ranges from the planet's origin 4.6 billion years ago to 3.8 billion years ago. Only a few Earth rocks are known that formed during the Hadean eon, and no fossils of Hadean age are known, making it impossible to subdivide the Hadean eon based on fossils. There are few fossils among the rocks of the Archean eon, and they are not preserved well enough to allow for finely tuned subdivision of this eon that spanned from 3.8 to 2.5 billion years ago. The fossil record does indicate that life began on Earth during the early Archean, and geologists recently have described fossilized algal structures, called stromatolites, in rocks as old as 3.45 billion years in Western Australia. More diverse groups of fossils have been found in sedimentary rocks of the Proterozoic eon, too. 5 billion to 543 million years ago. The most complex are multicellular and have different kinds of cells arranged into tissues and organs. A few types of Proterozoic shell-bearing organisms have been identified, but shelled organisms did not become abundant until the Paleozoic era. The Phanerozoic eon sedimentary rocks of the Phanerozoic eon, which covers the most recent 543 million years of geologic time, contain abundant fossils. Additionally, sedimentary rock and sediments of Phanerozoic age are very widely exposed on all of Earth's continents and form much of the superficial geology upon which human civilization exists. In North America, Phanerozoic sediments and sedimentary rocks make up nearly all surface exposures from the Florida Keys to the San Juan Islands of Washington State, and from Southern California to the tip of Cape Cod. Because they are widely exposed and literally form much of the ground immediately under our feet, Phanerozoic sedimentary rocks in North America and Europe, where the science of geology was born, have long been studied. The number of species with shells and skeletons dramatically increase, but the total number of individual organisms preserved as fossils increased as did the total number of species preserved as fossils. In rocks of earliest Phanerozoic time and younger, the most abundant fossils are the hard, tough shells and skeletons. Subdivision of the Phanerozoic eon into 3 eras is based on the most common types of life during each era. Sedimentary rocks that formed during the Paleozoic era contain fossils of early life forms, such as invertebrates, fishes, amphibians, reptiles, ferns, and cone-bearing trees. The Paleozoic era ended abruptly about 252 million years ago when the terminal Permian mass extinction wiped out 90% of all marine species, 2/3 of reptile and amphibian species, and 30% of insect species. In North America, rocks of Paleozoic age are widespread. Almost all of the bedrock geology of the New England states is Paleozoic in age. In New York State, only the bedrock of the Adirondack Mountains is not Paleozoic. Paleozoic bedrock also occurs widely across the mid-continent in Oklahoma, Missouri, Illinois, Indiana, Ohio, and West Virginia, and surrounding states including Pennsylvania, Tennessee, Iowa, Minnesota, and Wisconsin. In addition to the mid-continent, Paleozoic age sedimentary rocks are widespread in the Appalachian Mountains and within the Rocky Mountains. In contrast, Paleozoic rocks are relatively uncommon in California, Oregon, and Washington. Because it occurs widely, Paleozoic rocks have been used in many industrial applications historically. For example, almost all of the limestone building stone quarried in the mid-continent region is Paleozoic in age, including the limestone from Indiana, used to face all federal buildings in the area called Federal Triangle, between Pennsylvania and Constitution Avenues and 14th Street in Washington, D.C. Rocks of Paleozoic age contain high-quality coal in the Appalachians, oil and gas in the mid-continent and Rocky Mountain regions. Sand of Paleozoic age from the mid-continent is being heavily used today to develop oil wells, a topic we will explore in the next chapter. The Mesozoic era is most famous for the dinosaurs that roamed the land. Mammals and flowering plants also evolved during this era. The Mesozoic era ended 66 million years ago with another mass extinction that wiped out the dinosaurs. In the United States, Mesozoic sedimentary rocks and sediments occur at the surface along the Atlantic coastal plain, the lower Mississippi Valley, and across large portions of the Great Plains and Rocky Mountain regions. During Mesozoic time, a marine seaway formed in North America, and the seaway, called the Cretaceous Interior Seaway, stretched from the Gulf of Mexico to the Arctic Ocean. Sediments deposited in the seaway formed sedimentary rocks belonging to the youngest of Larry Sloss's formerly named marine sequences. He called it the Tagus sequence, after the widespread exposures of Mesozoic rock in the Texas region. During the Cenozoic era, mammals and grasses became abundant. Humans have evolved and lived entirely in the Cenozoic era. In the United States, almost all of the unconsolidated sediment that occurs at the surface is Cenozoic in age, including widespread glacial deposits across the northern states. Sedimentary rock and sediment of Cenozoic age covers the entire surface of Florida and Louisiana, and all of the geology of the Hawaiian Islands is Cenozoic in age. Cenozoic sediments also occur widely across other southeastern and Gulf Coast states, in a large swath across the Great Plains, within the broad valleys of the Rocky Mountain states and across far western states. The eras of Phanerozoic time are subdivided into periods, the time unit most commonly used by geologists. Some of the periods are named after special characteristics of the rocks formed during those periods. For example, the Cretaceous period is named from the Latin word for chalk, after chalk beds of this age in Africa, North America, and Europe. Other periods are named for the geographic localities where rocks of that age were first described. For example, the Jurassic period is named for the Jura Mountains of France and Switzerland. The Cambrian period is named for Cambria, the Roman name for Wales, where rocks of this age were first studied. In addition to the abundance of fossils, another reason that details of Phanerozoic time are better known than those of Precambrian time is that many of the older rocks have been deformed, metamorphosed, and eroded. It is simple probability that the older a rock is, the greater the chance that metamorphism or erosion has destroyed the rock or the features that record Earth's history. Chapter 5, Geologic Resources. Introduction. Since human-like creatures emerged 5 to 7 million years ago, our use of geologic resources has become increasingly sophisticated. Early hominids used sticks and rocks as simple weapons and tools. Later prehistoric people used flint and obsidian to make more effective weapons and tools, and they used natural pigments to create elegant art on cave walls. About 8000 BCE, people learned to shape and fire clay to make pottery. Archaeologists have found copper ornaments in Turkey dating from 6500 BCE. 1,500 years later, Mesopotamian farmers used copper farm implements. Today, geologic resources provide iron for steel, silicon for making computer chips, and gasoline that powers most cars. We use two types of geologic resources: mineral resources and energy resources. Mineral resources include all useful rocks and minerals. As we will see in the sections that follow, many mineral resources are naturally concentrated by processes that involve interactions among rock of the geosphere, atmospheric gases, and water from the hydrosphere. Humans have mined and refined these resources further to create the industrial world that has altered our planet. The primary energy resources of the early 21st century are coal, petroleum, and natural gas, all formed from the decayed remains of prehistoric plants and animals that have been altered by Earth systems processes. Mineral resources include both metal ore and non-metallic minerals. Recall from Chapter 2 that ore is rock sufficiently enriched in one or more minerals to be mined profitably. Geologists usually use the term to refer to metallic mineral deposits, and it is commonly accompanied by the name of the metal, for example, iron ore or silver ore. Non-metallic mineral resources refer to the useful rocks or minerals that are not metals, such as salt, building stone, sand, and gravel. When we think about striking it rich from mining, we usually think of gold. In 2016, the most recent year for which figures are available, the USGS estimated that the value of all the gold mined in the United States that year was $8.5 billion. However, the USGS also estimated in 2016 that more revenue was generated from mining gravel, sand, and crushed rock in the United States. Sand and gravel are mined from stream and glacial deposits, sand dunes, and beaches, whereas crushed stone is quarried from non-weathered igneous, metamorphic, or sedimentary bedrock. These non-metallic resources are mixed with Portland cement, a material produced by heating a mixture of crushed limestone and clay, to make concrete. Reinforced with steel, concrete is used to build roads, bridges, and buildings. Thus, reinforced concrete is one of the basic building materials of the modern world. In addition, many buildings are faced with stone, usually granite or limestone. Marble, slate, sandstone, and other rocks used for building are also mined from quarries cut into bedrock. There are many important metals and other elements that are fundamental parts of our lives and of the industries that produce a range of products in daily use. Some of these metals are familiar to us, such as iron, lead, copper, aluminum, silver, and gold. Others are less well known, such as molybdenum, tungsten, and borax. All mineral resources are non-renewable. We use them up at a much faster rate than natural processes create them, although many can be recycled. Gold, for example, has been extracted and used by humans for over 6,000 years, and today gold mines exist all over the world and on every continent except Antarctica. The gold has accumulated in different types of deposits in different locations over geologic time. Most individual gold deposits take hundreds of thousands or millions of years to develop, and many were formed millions of years ago. According to Thomson Reuters GFMS, a major source of investment information for metals, if all the world's gold that has been mined by humans could be combined into a single giant cube, it would have sides that are 27 m long, corresponding to 171,300 metric tons. Other estimates vary but are generally in the same ballpark. Although it might seem that most gold has already been found, the USGS estimates that roughly 52,000 more metric tons exist in gold deposits that are not yet discovered, suggesting that gold will be mined for many years to come. Gold is easily recycled through melting and has been recycled for millennia. In fact, almost all of the gold mined throughout history is still being used today. Your grandfather's gold watch may include some gold mined by the Romans 2,000 years ago. The recent increase in technology changes this long tradition of recycling gold, however, because in many applications the amount of gold used is so small so as to make recycling non-economic and thus impractical. As a result, for the first time in human history, gold is being consumed. Gold represents an extreme example because it is so easily remelted and recycled and has held its value for so long. In almost all other cases, mineral ore extracted from the earth is consumed at higher rates than gold. For example, much of the iron that is extracted from the earth and concentrated to make steel is not recycled but rather simply is consumed and ultimately ends up in a landfill. Figure 5.2, ORE and ORE deposits. If you pick up any rock and send it to a laboratory for analysis, the report will probably show that the rock contains measurable amounts of iron, gold, silver, aluminum, and other valuable metals. However, the natural concentrations of these metals are so low in most rocks that the extraction cost would be much greater than the income gained by selling the refined metals. In certain locations, however, natural geologic processes have enriched metals many times above their normal concentrations. Table 5. 1 shows that the natural concentration of a metal in or may exceed its average abundance in ordinary rock by a factor, called the enrichment factor, of more than 100,000. Successful exploration for new ore deposits requires an understanding of the processes that concentrate metals to form ore. For example, platinum concentrates in certain types of igneous rocks. Therefore, if you were exploring for platinum, you would focus on those rocks rather than on sandstone or limestone. With the exception of magmatic processes, which occur deep within the crust, the natural processes that concentrate ore minerals all involve interactions of rocks and minerals of the geosphere with water from the hydrosphere. The more common ore-forming processes are described below. Magmatic processes. Magmatic processes form mineral deposits as liquid magma solidifies to form an igneous rock. These processes create metal ores as well as some gems and non-metallic mineral deposits including sulfur deposits and building stone. Some large bodies of plutonic igneous rock, particularly those of mafic composition, solidify in layers. Each layer contains different minerals and is of a different chemical composition than adjacent layers. Some of the layers may contain rich ore deposits. The layering can develop by at least two processes. 1. Cooling magma does not solidify all at once. Instead, higher temperature minerals crystallize first, and lower temperature minerals form later as the magma cools and the temperature drops. Most minerals are denser than magma. Consequently, early formed crystals may sink to the bottom of a magma chamber in a process called crystal settling. In some instances, ore minerals crystallize with other early formed minerals and accumulate in layers near the bottom of a pluton. 2. Some large bodies of mafic magma crystallize from the bottom upward. Thus, early formed ore minerals become concentrated near the base of the pluton. The largest ore deposits found in layered mafic plutons are the rich chromium and platinum reserves of South Africa's Bushveld intrusion. The pluton is about 375 by 300 kilometers in area, roughly the size of the state of Maine, and about 7 kilometers thick. The Bushveld deposits contain more than 20 billion tons of chromium and more than 10 billion grams of platinum, the greatest reserves in any known deposit on Earth. The platinum alone is worth roughly $300 billion at 2018 prices. Hydrothermal processes, hydro for water and thermal for heat. Involving interactions between hot water or steam and rocks or minerals, are probably responsible for the formation of more ore deposits, and a larger total quantity of ore than all other processes combined. To form a hydrothermal ore deposit, hot water dissolves metals from rock or magma. The metal-bearing solutions then seep through cracks or through permeable rock, where they precipitate to form an ore deposit. Although water by itself is capable of dissolving minerals, most hydrothermal waters also contain dissolved salts. The presence of the salts greatly increases the water's ability to dissolve minerals. Therefore, hot, salty, hydrothermal water is a very powerful solvent, capable of dissolving and transporting metals. Hydrothermal water comes from three sources: granitic magma, groundwater, and the oceans. 1. Granitic magma contains more dissolved water than solid granite rock. Thus, the magma gives off hydrothermal water as it solidifies. Because many ore metals do not fit neatly into the crystal structure of silicate minerals that form from a cooling granitic magma, these elements become concentrated in the hydrothermal waters. 2. Groundwater can seep into Earth's crust, where it is heated and forms a hydrothermal solution. The solution circulates through rock in the crust and dissolves ore metals, which later precipitate in concentrated form elsewhere. This scenario is common in volcanic areas where hot rock or magma heat groundwater at shallow depths. 3. In the oceans, hot, young basalt at a mid-oceanic ridge heats seawater as it seeps into cracks in the seafloor. Refer again to Table 5.1, which shows that tiny amounts of all metals are found in average rocks of the Earth's crust. For example, gold makes up 0.000002% of the crust, while copper makes up 0.0058% and lead 0.0001%, although the metals are present in very low concentrations in country rock. Hydrothermal solutions percolate through vast volumes of rock, dissolving or scavenging the metals and carrying them in solution. Where they encounter changes in temperature, pressure, or chemical environment, the solutions then can deposit the metals to form a local ore deposit. A hydrothermal vein deposit forms when dissolved metals precipitate in a fracture in rock. Ore veins range from less than a millimeter to several meters in width. A single vein can yield several $1 million worth of gold or silver. The same hydrothermal solutions may also soak into pores in country rock near the vein to create a large but much less concentrated disseminated ore deposit. Because they commonly form from the same solutions, rich ore veins and disseminated deposits are often found together. The history of many mining districts is one in which early miners dug shafts and tunnels to follow the rich veins. After the veins were exhausted, later miners used huge power shovels to extract low-grade ore from disseminated deposits surrounding the veins. In volcanically active regions of the seafloor, near mid-ocean ridges and submarine volcanoes, seawater circulates through the hot, fractured oceanic crust. The hot seawater dissolves metals from the rocks and then, as it rises through the upper layers of oceanic crust, cools and precipitates the metals to form submarine hydrothermal ore deposits. The metal-bearing solutions can be seen today as jets of black water, called black smokers, spouting from fractures and vents in the mid-oceanic ridge. The black color is caused by precipitation of fine-grained metal sulfide minerals as the solutions cool upon contact with seawater. The precipitating metals accumulate as chimney-like structures near the hot water vent. Rich ore deposits form in such environments, but the cost to operate machinery in such great water depths is prohibitive. Sedimentary processes placer. Deposits gold is denser than any other mineral. Therefore, if you swirl a mixture of water, gold dust, and sand in a gold pan, the gold sinks to the bottom fastest. Differential settling also occurs in nature. Many streams carry silt, sand, and gravel with an uncommon small grain of gold. The gold settles fastest when the current slows down. Over years, currents agitate the sediment and the dense gold works its way into cracks and crevices in the streambed. Thus, grains of gold concentrate in gravel as well as in cracks and potholes eroded into the bedrock of the streambed, forming a placer deposit. The prospectors who rushed to California in the gold rush of 1849, for example, mined placer deposits in conglomerate of Eocene age there. Precipitates groundwater dissolves minerals as it seeps through soil and bedrock. In most environments, groundwater eventually flows into streams and then to the sea. Some of the dissolved ions, such as sodium and chloride, make seawater salty. In deserts, however, playa lakes develop with no outlet to the ocean. Water flows into the lakes but can escape only by evaporation. As the water evaporates, the dissolved salts concentrate until they precipitate to form evaporite deposits. The composition of the salt and specific salt minerals that form depend on the composition of dissolved ions transported to the basin, which in turn depend upon the bedrock in the region. Evaporite deposits in desert lakes include sodium chloride, borax, sodium sulfate, and sodium carbonate. These salts are used in the production of paper, soap, and medicines and for the tanning of leather. Several times during the past 500 million years, shallow seas covered large regions of North America and all other continents. At times, those seas were so weakly connected to the open oceans that water did not circulate freely between seas and the oceans. Consequently, evaporation concentrated the dissolved salts until they precipitated as marine evaporites. Periodically, new seawater from the open ocean would replenish the shallow seas, providing a new supply of salt. Thick marine evaporite beds, formed in this way, underlie much of North America. Table salt, gypsum, and potassium salts are mined extensively from these deposits. Most of the world's supply of iron is mined from sedimentary rocks called banded iron formations, which are deposits composed of alternating iron-rich and silica-rich layers. These iron-rich rocks precipitated from the seas between 2.6 and 1.9 billion years ago, as a result of rising atmospheric oxygen concentrations. Weathering processes in environments with high rainfall, the abundant water dissolves and removes most of the soluble ions from soil and rock near Earth's surface. This process leaves the relatively insoluble ions in the soil to form residual or deposits. Both aluminum and iron have very low solubilities in water. Bauxite, the principal source of aluminum, forms as a residual deposit, and in some instances iron also concentrates enough to become ore. Most bauxite deposits form in warm and rainy tropical or subtropical environments where chemical weathering occurs rapidly. Thus, bauxite ores are common in Jamaica, Cuba, Guinea, Australia, and parts of the southeastern United States. Mineral reserves versus mineral resources. Mineral reserves are the known amount of ore in the ground that can be mined profitably. Reserves represent a working inventory of an economically extractable mineral commodity in a particular mine or on a national or global scale. Mineral resources, described at the beginning of this chapter, are all occurrences of a mineral commodity, including those only surmised to exist, that have present or anticipated future value. Mining depletes mineral reserves by decreasing the amount of ore remaining in the ground, but reserves may also increase in two ways. First, geologists may discover new mineral deposits, thereby adding to the known amount of ore. Second, subeconomic mineral deposits, those in which the metal is not sufficiently concentrated to be mined at a profit, can become profitable if the price of that metal increases or if improvements in mining or refining technology reduce extraction costs. For example, in 1970, world copper resources, including all identified and undiscovered sources, were estimated at 1.6 billion metric tons. World reserves of copper, that portion of copper resources that could be profitably extracted, were estimated at only 280 million metric tons. Between 1970 and 2010, however, improved mining techniques and rising copper prices resulted in the production of about 400 million metric tons of copper, nearly 43% more than the 1970 global reserve estimate. Moreover, these two factors, improved technology and rising prices along with a continued strong demand, have driven the exploration and production of new copper sources. The strong and accelerating demand for copper exists because of the metal's excellent alloying properties, which have made it exceptionally valuable when combined with other metals, such as zinc, tin, or nickel, which is especially resistant to corrosion by marine waters. Cupronickel also reduces the adhesion of marine life, such as barnacles, to boat hulls, thereby reducing drag and increasing fuel efficiency. Brass is more malleable and has better acoustic properties than pure copper or zinc. Consequently, it is used in a variety of musical instruments, including trumpets, trombones, bells, and cymbals. Bronze are especially fluid in the molten state and so are well suited to casting because the metal flows into the nooks and crannies of the mold before solidifying. In fact, bronze has so long been used by humans that the so-called Bronze Age corresponds to the dates between about 3500 BC and 1200 AD, when bronze represented society's technological cutting edge for over 4 millennia. Only when humans began to develop the ability to forge an even stronger metal, iron, did the Bronze Age of civilization end. Today, copper wiring and plumbing are integral to the appliances, heating and cooling systems, and telecommunications links used every day in homes and businesses. Copper is used in the transmission of electricity and is an essential ingredient for alloys used to make motors, radiators, connectors, brakes, and bearings used in cars and trucks. According to the USGS, the amount of copper in an average modern car ranges from 20 kilograms in small cars to 45 kilograms in luxury and hybrid vehicles. Clearly, copper will continue to be a vital mineral resource to human society for long into the future. The geopolitics of metal resources. Earth's mineral resources are unevenly distributed, and no single nation is self-sufficient in all minerals. Moreover, as technology evolves, the value of mineral and energy resources can change drastically. For example, salt was once used as currency. It drove the establishment of trade routes, caused armed conflicts between the Vatican and its subjects in Perugia in 1540, and was at the source of a 12-year-long armed struggle along the Texas-Mexican border in the 1860s and 1870s. The discovery of large salt deposits and development of refrigeration since then has significantly reduced the strategic value of salt. Similarly, the discovery and refinement of large petroleum reserves has eliminated the strategic value of whale oil. Historically, 5 nations, the United States, Russia, South Africa, Canada, and Australia, have supplied most of the mineral resources used by modern societies. However, today, China is the world's leading producer of many mineral resources, including aluminum, gold, iron, lead, phosphate rock, tin, tungsten, and zinc. China is also the world's leading exporter of several mineral resources, including antimony, barite, graphite, tungsten, and rare earth metals critical to defense and other high-tech industries. Although it is the lead producer and exporter of many mineral resources, China is also the world's largest consumer of many mineral commodities and has embarked on a strategic policy of purchasing the rights to many large mineral deposits around the world. Today, China's domestic supply and demand for various mineral commodities is high enough to directly affect the world mineral markets. Many other nations have few mineral resources. For example, Japan has almost no metal or fuel reserves. Despite its modern economy and high productivity, it relies entirely on imports for metals and fuel. Currently, the United States depends on dozens of other countries for the majority of its mineral consumption. According to the USGS, in 2017, the United States was 100% dependent on imports for as many as 21 different mineral commodities. Many of these commodities are important in the high-tech, communications, and defense industries. Examples include yttrium, essential for microwave communications equipment, cobalt, a critical metal alloy, and vanadium, essential for the manufacture of supercomputers. Because of the United States' dependence on many mineral and metal imports, the U.S. government has maintained stockpiles of various strategic mineral commodities. Figure 5.11 shows a list of 64 mineral commodities and the percentage upon which the United States relies on imports for each. Mines and mining miners extract both ore and coal from underground mines and surface mines. A large underground mine may consist of tens of kilometers of interconnected passages that commonly follow ore veins or coal seams. The lowest levels may be several kilometers deep. In contrast, a surface mine is a hole excavated into Earth's surface. The largest human-created excavation on Earth is the open-pit copper mine at Bingham Canyon, Utah. It is 4 kilometers in diameter and 1.2 kilometers deep and can be seen with the unaided eye from space. Since its beginning in 1873, the mine has produced about 14.5 million tons of copper, along with significant amounts of gold, silver, and molybdenum. Most modern coal mining is done by large power shovels that extract coal from huge surface mines. In the United States, the Surface Mining Control and Reclamation Act of 1977 requires mining companies to restore mined land so that it can be used for the same purposes for which it was used before mining began. In addition, a tax is levied to make it possible to reclaim land that was mined before the law was enacted. Enforcement and compliance of environmental laws waxes and wanes with the political climate in Washington. Yet environmental awareness has increased dramatically over the past generation, and, overall, mining operations pollute much less today than they did 50 years ago. One of the big challenges for the future is to clean up old mines that were operated under lax or non-existent environmental regulations of the past. In the United States, more than 6,000 unrestored coal and metal surface mines cover an area of about 90,000 square kilometers, almost as large as the state of Virginia. This figure does not include abandoned sand and gravel mines and rock quarries. Although underground mines do not directly disturb the land surface, some abandoned mines collapse, and occasionally buildings have sunken into the resulting holes. Over 800,000 hectares of land in central Appalachia have settled into underground coal mine shafts. Mining of both metal ores and coal also creates huge piles of waste rock that must be removed to get at the ore or coal or that is left over after the refining of the ore. If the waste piles are not treated properly, rain erodes the loose rock and leaches toxic elements such as arsenic, sulfur, and heavy metals from the piles, choking the streams with sediment and polluting both stream water and groundwater. Energy resources: coal, petroleum, and natural gas. Coal, petroleum, and natural gas are called fossil fuels because they formed from the remains of plants and animals. Fossil fuels are not only non-renewable but also unrecyclable. When a lump of coal or a liter of oil is burned, the energy dissipates and is, for all practical purposes, lost. Thus, our fossil fuel supply inexorably diminishes. Coal is a sedimentary rock made mostly of organic carbon, enough that the rock will burn without refining. Coal-fired electric generating plants burn about 92% of the coal consumed in the United States and produce slightly less than 50% of the nation's electricity. Although it is easily mined and abundant in many parts of the world, coal emits air pollutants that can be removed only with expensive control devices. Mercury, in particular, is released into the atmosphere mainly through coal-fired power plants. Despite these drawbacks, coal is an abundant resource, with widespread availability projected to last beyond the 21st century. In North America, large quantities of coal formed during the Carboniferous period, between 360 and 286 million years ago, and later in Cretaceous and Paleocene times, when warm, humid swamps covered broad areas of low-lying land. When plants die in forests and grasslands, organisms consume some of the plant litter, and chemical reactions with oxygen and water decompose the remainder. As a result, little organic matter accumulates, except in the topsoil. In some swamps and bogs, however, plants grow and die so rapidly that newly fallen vegetation quickly buries older plant remains. The new layers prevent atmospheric oxygen from penetrating into the deeper layers, and decomposition stops before it is complete, leaving brown, partially decayed plant matter called peat. Plant matter is composed mainly of carbon, hydrogen, and oxygen and contains large amounts of water. During burial, rising pressure expels the water and chemical reactions release most of the hydrogen and oxygen. As a result, the proportion of carbon increases until coal forms. The grade of coal and the heat that can be recovered by burning coal can vary considerably depending on the carbon content. Table 5.2 compares the amount of heat that can be produced by different grades of coal, compared to petroleum-based fuels, discussed next. Petroleum. The word petroleum comes from the Latin for rock oil or oil from the earth. Some natural oil seeps in Asia were used at least as long ago as Alexander the Great, and oil wells in China were hand-dug with bamboo poles in 347 CE. In North America, the first commercial oil well was drilled in Titusville, Pennsylvania, in 1859, ushering in a new energy age. Crude oil, as it is called when pumped from the ground, is made up of thousands of different chemical compounds and ranges widely in consistency and color. Some petroleums are brown, waxy substances that are solid at room temperature but liquid at higher temperatures that exist within the Earth's crust. Some petroleums are yellowish or nearly clear liquids that resemble refined gasoline. Most are rather thick and dark-colored. Once recovered from a well, crude oil is refined to produce propane, gasoline, heating oil, and other fuels. Petroleum also is used to manufacture plastics, nylon, and other useful materials. Formation of petroleum. Petroleum forms from the accumulation of large quantities of organic matter in muddy sediment deposited in swamps, lakes, and marine waters. Most of the organic matter comes from algae, plant remains, and bacteria. Over millions of years, younger sediment buries this organic-rich mud to depths of a few kilometers, where rising temperature and pressure convert the mud to shale. At the same time, the elevated temperature and pressure cause the organic matter to convert to a solid organic substance called kerogen. At temperatures ranging from 50 degrees Celsius to about 160 degrees Celsius, the kerogen breaks down chemically, liberating small organic molecules. These organic molecules form petroleum. The shale or other sedimentary rock in which oil originally forms is called the petroleum source rock. With time, some of the organic molecules in the source rock are expelled as liquid petroleum that seeps into the pore spaces in adjacent rock layers. Because petroleum is less dense than water in the pore spaces, the petroleum rises toward the surface through the network of pores in the rock. If it is not trapped along the way, the oil will migrate all the way to the surface, forming a natural oil seep. The La Brea tar pits in downtown Los Angeles is perhaps the most famous example of a natural oil seep. Between 40,000 and 8,000 years ago, over 660 species of organisms became trapped in tar formed from the La Brea oil seeps, died, and were preserved. In many circumstances, migrating petroleum will not reach the surface but rather will become trapped in a conventional petroleum reservoir. A conventional reservoir consists of oil-saturated porous rock that is like an oil-soaked sponge. It is not an underground pool or lake of oil. Many conventional reservoirs form when the rising oil is trapped by an overlying layer of impermeable rock, that is, rock through which liquids do not pass quickly because the pore spaces are too small or are otherwise big enough but not interconnected, as with the isolated holes in Swiss cheese. To extract petroleum from a conventional reservoir, an oil company drills a well into it. After the hole has been bored, the expensive drill rig is removed and replaced by a smaller rig that sets pipe in the borehole and perforates the pipe adjacent to oil-bearing layers so that the oil can flow from the rock into the pipe. Following this, a pump jack is installed to draw the petroleum up the pipe. 50 years ago, many conventional reservoirs lay near the surface and oil was easily pumped from shallow wells. But these reserves have been largely depleted, causing many modern oil companies to seek deeper reservoir targets, sometimes below the seafloor in water up to 3 kilometers deep. Primary recovery techniques utilize the pressure in a conventional reservoir to push oil into the wellbore. As oil is removed, however, this pressure decreases to the point at which the remaining oil cannot be drawn into the wellbore. On average, more than half of the oil in a reservoir is too viscous to be pumped to the surface by conventional techniques and is left behind when the oil field has gone dry. Additional oil can be extracted by secondary and tertiary recovery techniques involving the injection of water, detergent, pressurized gas, or other fluids into the reservoir. Secondary methods are employed first, and when those are exhausted, tertiary methods are used. In one simple secondary process, water is pumped into one well, called the injection well. The pressurized water floods the reservoir, driving oil to nearby wells, where both the water and oil are extracted. At the surface, the water is separated from the oil and reused, while the oil is sent to the refinery. One tertiary process pumps detergent into the reservoir. The detergent dissolves the remaining oil and carries it to an adjacent well, where the petroleum is then recovered and the detergent recycled. Because an oil well location occupies only a few hundred square meters of land, most cause relatively little environmental damage. However, oil companies are now extracting petroleum from fragile environments such as the ocean floor and the Arctic tundra. To obtain oil from the seafloor, engineers build platforms on pilings driven into the ocean floor and mount drill rigs on these steel islands or use a drilling platform that floats but maintains its position through powerful stabilizing motors controlled by a precise GPS system. Despite great care, accidents occur during the drilling and extraction of oil. In 2010, the largest accidental marine oil spill in the history of the petroleum industry took place in the Gulf of Mexico when a blowout occurred on the seafloor below the Deepwater Horizon oil platform. The seafloor blowout caused an explosion on the drilling platform that killed 11 workers and injured 17 others. For 3 months, oil gushed uncontrollably from the seafloor before the well was finally capped and declared dead. By then, however, an estimated 4.4 million barrels of oil had been released into the environment. The oil spread throughout much of the Gulf of Mexico, poisoning marine life and disrupting marine and coastal ecosystems. Natural gas is an energy resource that forms in source rock or an oil reservoir when crude oil is heated above 100 degrees Celsius during burial and causes the organic molecules to break down to methane, CH, an organic molecule consisting of a single carbon atom bonded to 4 hydrogen atoms. Many conventional petroleum reservoirs contain a layer of oil-saturated rock, with a layer of gas-saturated rock above the heavier liquid petroleum. Other conventional reservoirs are saturated only by gas. Natural gas is used without refining for home heating and cooking and for fueling large electricity generating plants. Because natural gas contains few impurities, it releases little sulfur or other pollutants when it burns, although, as with all fossil fuels, combustion of natural gas releases carbon dioxide, a greenhouse gas. This fuel produces fewer pollutants and is less expensive to produce than petroleum.